Hi everyone, we are going to finish up chapter 5, which was all about the idea of integration and estimating integrals by going back to the idea of estimating an integral using a Riemann sum. And this Riemann sum requires the use of trapezoids instead of rectangles. So before we get started on that, I want to remind everybody about the previous methods we used for estimating integrals, and that was the rectangular approximation methods. And if you recall, those are either an overestimate or an underestimate if we're using LRAM or RRAM. And I don't recommend remembering these two statements up here. I recommend drawing yourself a curve and figuring out what the situation is. But nevertheless, if a function f of x is increasing on a closed interval, then left n or LRAM underestimates the integral from a to b of f of x dx, and right or RRAM overestimates the integral from a to b of f of x dx. If, however, f of x is decreasing on that closed interval, then LRAM overestimates the integral and RRAM underestimates it. Again, I don't recommend memorizing those. I recommend drawing yourself a picture of that. The last method that we're going to talk about here is related to LRAM and RRAM, but it requires drawing trapezoids. And if you remember from your days in geometry, the formula for the area of a trapezoid is the sum of the two bases, or the average of the two bases, which are the two segments or two sides that are parallel to each other. Those are the two bases. Either one could be A, either one could be B. Divided by 2 times the height, and the height is always perpendicular to the two bases. So as an example here, we are going to use 3 trapezoids to approximate the integral from 0 to 3 of x cubed dx. So just to be clear, our trapezoids are formed by these vertical segments at x equal 1, 2, 3, and you could say there's a segment at 0. We'll talk about that in a moment. The heights are going to be the distances between those. So we'll draw those heights in there. And so each one of these intervals is the height. And we're going to connect these segments with one of the non-parallel sides of the trapezoid. And the height would form the other non-parallel side. The first trapezoid right here is technically a triangle, but if you take a look at the formula for the area of a trapezoid, and we said that we have 0 plus b divided by 2 because the first parallel side has a height of 0 at x equals 0 times the height, we would get the base divided by 2 times the height, or 1/2 base times height, which is the area of a triangle. So it all takes care of itself in the end. So let's go through the process of estimating the integral from 0 to 3 of x cubed dx using the trapezoid rule. So the integral from 0 to 3 of x cubed dx is approximately equal to, well, we're going to take 0 cubed, which establishes the height of the first parallel side of the first trapezoid, plus 1 cubed, we're using the function there to establish the heights, the lengths of the two bases, divided by 2 times the height, which is 1 in this case. And the height, again, is the distance between the x values, plus 1 cubed plus 2 cubed divided by 2 times 1, plus 2 cubed plus 3 cubed divided by 2 times 1. And that you probably recognize as the first base only occurring once and the last base occurring once, but the two bases in between occurring twice. So if you go through this process, what you have is, if we're going to group these two together, we're going to factor out the 1/2. We have 0 cubed plus 2 times 1 cubed plus 2 times 2 cubed plus 3 cubed, and we can do it that way. As long as the heights are the same, we can do that. And we have 1/2 times 0 plus 1 plus 16 plus 27. And if you simplify that, you get 22 and 1/2. So there's an example of how to use the trapezoid rule to estimate an integral. So as before, when we were using LRAM and RRAM, we often ask ourselves the question, is this an overestimate or an underestimate? And to answer that question, you kind of have to zoom in on this picture a little bit and take a look at the lengths, or not the lengths, but these segments right here, the non-parallel sides. And you can tell when you look at that those areas of those trapezoids are bigger than the area between the function and the x-axis on those intervals. So in this case, the trapezoid rule overestimates, so it's an overestimate. Now the question is, under what circumstances does the trapezoid rule overestimate an integral? Under what circumstances does it underestimate the integral? So pause the video for a minute and see if you can come up with an answer to this next question. So if you said that the trapezoid rule overestimates the integral when the function f of x is concave up on the closed interval, then you are correct. And it underestimates the integral when f of x is concave down on the closed interval. Again, I would not try and memorize that. I would draw myself a picture of a function like this one here, which illustrates the idea that the trapezoid rule is overestimating the integral when the function is concave up. And you'll just see a similar thing when the function is concave down. So the next thing I'd like to do is to use the trapezoid rule to estimate a few integrals. In these two examples, we are going to approximate these integrals using 4 equal subintervals and then determine whether or not the estimate is an over or underestimate. So let's start out with this first integral, the integral from 1 to 3 of 1 over x dx. Having a good idea of what functions generally look like is really helpful here. So we're going to graph this thing. 1 over x function looks like this on the interval from 1 to 3. 1, we'll make that 2, we'll make that 3. We're going to do 4 equal subintervals. So there's 1.5, and then there's 2 and 1/2. And therefore, our heights are going to be equal to 1/2. Recall, the height of a trapezoid is the distance between the two parallel sides. So let's draw these trapezoids in. Drawing the parallel sides first, and the heights in here. And now we'll draw in the non-parallel side. And it's a little hard to see, but our function is concave down on this interval, so those sides that I just drew in are going to be higher than the actual function value on each of those intervals. So this should be an overestimate. So our integral from 1 to 3 of 1 over x dx is going to be approximately equal to, well, we have to find each of the heights, of each of the bases. So, if we call this A and then B and so on and so forth, it's going to be the value of the function to establish the length of each of the bases. So 1 over 1 plus 1 over 1 and 1/2 all over 2. That's A plus B divided by 2 times the height of 1/2 plus 1 over 1 and 1/2 plus 1 over 2. Again, the lengths of the two bases divided by 2 times the height of 1/2 plus 1 over 2 plus 1 over 2 1/2 divided by 2 times the height of 1/2, and then finally plus 1 over 2 1/2 plus 1 over 3, all divided by 2 times 1/2. Now we're not going to go through the algebra of simplifying all that. I'm just going to tell you that if you do all of that, you will end up with a value of 1.117, and that should be an overestimate of the integral from 0 to 3 of 1 over x dx, because 1 over x is concave up on the closed interval from, sorry, I said 0 to 3, 1 to 3. Don't forget, you got to be able to justify those reasons there as well. And you can verify that that's an overestimate, and you can verify that value that we got for our estimate using your calculator. In the next example, we are going to find the integral from 0 to 4 of the square root of x dx. So again, let's sketch ourselves a graph of this function. This function looks like this on the interval from 0 to 4. So 0, 1, 2, 3, 4. Those are our subintervals. So our height is going to be 1 in each of these, and our trapezoids look like this. And if you can see, the non-parallel bases that I'm drawing in right now are below the function value, so this should be an underestimate. So our integral from 0 to 4 of the square root of x dx is going to be estimated using the trapezoid rule by finding each of the bases. Those are the parallel sides, and the first one is technically a triangle, but the formula for the area of a trapezoid works for a triangle. So we have 0 plus 1, or the square root of 0 plus the square root of 1 all over 2 times 1 plus the square root of 1 plus the square root of 2 over 2 times 1 plus the square root of 2 plus the square root of 3 all over 2 times 1, and then finally plus the square root of 3 plus the square root of 4 all over 2 times 1. And again, I want to remind you that if the heights of the trapezoids are equal, you can do some algebra and factor out this part right here and recognize that only the first and the last bases occur once and all the others occur twice. So you could do something like this: 1/2 times the square root of 0, 0 plus 2 times the square root of 1 plus 2 times the square root of 2 plus 2 times the square root of 3 plus the square root of 4, if you had any need to do that. And if you do that, you end up with the following: 5.146, and this should be an underestimate because the square root of x is concave down on the closed interval from 0 to 4. Again, don't try and memorize that rule. Just draw yourself a picture and figure it out from there. Just like when we're using the rectangular approximation method, we often have situations using the trapezoid method where the intervals or subintervals are not the same length. So in the last couple examples we're going to deal with that situation. So here's the scenario. As you know, the temperature in room 103 fluctuates quite a bit during the day. And I would like to make the argument that the average temperature in the room is too cold. Average temperature. So how am I going to do that? I have this data for various times during the day, which is the time and the temperature in the room. And I want to estimate, using the trapezoid rule, the average temperature throughout the day. So if you recall, the average temperature, or the average value of a function, is equal to the integral from a to b of f of t dt divided by the length of that interval. And so we're going to estimate the integral, and then we're going to divide it by the length of that interval to estimate the average temperature in my classroom on this particular day. So in our table up above, what we're going to do is we're going to use t as our variable on our horizontal axis. We'll call 7 a.m. t equals 0. So 9 a.m. would be t equal 2, 10 a.m. would be t equal 3, and 1 p.m. would be 3 hours later, so that would be t equals 6, and an hour after that, t equals 7, and 2 hours after that, t is equal to 9. As you can see, the differences in these times are not all the same. So from 0 to 2, we have 2. From 2 to 3, we have 1. 3 to 6, we have 3. 6 to 7, we have 1. And 7 to 9, we have 2. Those establish the heights of our trapezoids. So let's go down to our graph here and draw these trapezoids in. And our first trapezoid is going to have that height right there, that base right there, that height right there from 0 to 2, and the other base right there. Second trapezoid, third trapezoid, fourth trapezoid, and our fifth trapezoid. The process is still the same. We're just using heights that are not equal. So in each of the trapezoids, we're going to find their areas. So by looking at the table, we can see that our first base is 53, our second base is 84. We divide that by 2 to find the average. As I was saying, our first trapezoid, we add up the two bases, divide by 2 to find the average, and then we multiply by the height. And the height in this case is the distance from 7 a.m. to 9 a.m., which is 2. In the next trapezoid, we have a height of 84 plus, I keep saying height, sorry, I mean a base of 84 plus a base of 73. Divide that by 2, multiply that by the height, which is 1 in this case. Our next trapezoid, kind of a big one, it has a base of 73 plus a base of 68. Divide that by 2 to find the average. The distance between those two bases is 3. The next one, base of 68 plus a base of 59. Divide that by 2 and multiply that by 1. And the last one, we have a base of 59 plus a base of 53. Divide that by 2 and multiply that by 2. And if we add up all of those trapezoids, the average value is going to be, well, first of all, from t equals 7 a.m. to t equals 4 p.m. is a difference of 9 hours. So we're going to divide that integral by 1/9, or divide it by 9. And this trapezoid method gives us a value of 602.25 degree Fahrenheit times hours, but the 9 is in hours, so the hours are going to cancel each other out, and so our average value is approximately 66.944 degrees Fahrenheit. Now you might ask yourself if this is an overestimate or an underestimate, and in this case you can't answer that question because we don't know if the temperature relationship is concave down or concave up on each of those intervals, so we don't know for sure. In this last example, we are going to use the trapezoid method to estimate the distance that a train travels. Now, you need to be careful in this situation because on the y-axis is the velocity. And as you know from first semester, if the velocity is positive, the train is traveling in a positive direction. But if it's negative, it's traveling in a negative direction. So if we just integrated this whole thing, we're going to have some positive accumulation for the velocity that's positive and some negative accumulation, and that total would not represent the distance traveled. So we need to use the idea of the area between the function and the x-axis to deal with this situation. So what do we have? We want to know approximately how far the train traveled during the 12-minute period. On the horizontal axis, we have time in minutes. On the vertical axis, we have velocity in meters per minute. And as you can see, our intervals are, let's see, 2, 3, 2, 1, and 4. So they are not equal intervals, therefore not equal heights for our trapezoids. So let's draw our trapezoids in. First trapezoid is technically a triangle. Second trapezoid is technically a triangle. Third trapezoid, technically a triangle. And the fourth is actually a real trapezoid. Now, you could break this up into triangles if you want, and we're actually going to do that because it kind of makes more sense to do it that way in this case. So the formula for the area of a triangle, 1/2 base times height. So in this case, 1/2 times the base from 0 to 7 is a total of 7, times the height of 100. The next triangle is going to be an area of 1/2 times the base of 1 times the height in this case. Well, we have to look at the value of the function at time 8, which is negative 120, and consider that positive for that area. And then finally the area of the trapezoid. So 120 plus 150, I'm taking the absolute value of the function at those two times of 8 and 12, divided by 2 times the height, which is 4. And now we're not going to treat the values, the areas underneath the x-axis as negative. We're going to treat everything as positive, and therefore we estimate the distance traveled when we add up all these areas to be approximately 950 meters. Again, don't force yourself to use a method like the trapezoid method if you can break it down into nice geometric shapes. There's no need. You do need to know how to use the trapezoid method, though. The last thing we're going to do is we are going to finish up with a look at the relationship between the trapezoid method and LRAM and RRAM. So here's some random function here, f of x, and we're going to take a look at just one interval from a to b, and we are going to draw in the left-hand rectangular approximation method, which would be shown here in black, so we'll call that LRAM. And then we're going to draw in the right-hand rectangular approximation method, which we are going to show here in green. So we'll call that RRAM. And then in blue, we will draw in the trapezoid method, which is basically just connecting those right there. So this is the trapezoid method. So the question is this: how is the trapezoid method related to LRAM and RRAM? Take a look at this picture, and pause the video, and see if you can figure out the relationship for this one rectangle. So if you were thinking something like this, so here's the black rectangle, and here is the green rectangle. I'll do my best to sketch all that in. And then we've got the trapezoid, which is going to be the blue, which is going to be there. So this is getting a little bit confusing. It's obvious that the trapezoid area is going to be somewhere between what we get using LRAM and RRAM. Well, here's what it turns out to be, that the trap method is equal to, well, it's halfway between LRAM and RRAM, because what we do, if we take a look at that rectangle up at the top, this part right here, we basically split that in half using the trapezoid method. So what do we get using the trapezoid method? We get the average of LRAM and RRAM. So RRAM plus LRAM divided by 2, or the average of RRAM and LRAM.